Okay, in this podcast we're going to take a look at how to determine the enthalpy of formation for a compound, both using a few different ways, including Hess's law. Okay, so let's talk about what enthalpy of formation is. The enthalpy of formation is the enthalpy change when 1 mole of a compound is made from its elements in their standard states. Okay, this naught means in the standard states. F is heat of formation, and because we're talking about forming something from its standard states, there's no need to form an element in its standard state. They're already formed. So for elements, the heat of formation would be 0. So let's take a look at how we would do this. Alright, so exercise 10 says, for each of the following compounds, write a balanced thermochemical equation depicting the formation of 1 mole of the compound from its elements in their standard states. Okay, so we have, let's start off, first one, we have ammonia, right? So in order to make ammonia, we have to form it from its elements. So it's going to form from nitrogen. In its standard state would be a gas, and hydrogen, and it would also be in its as a gas, okay, as an element. And as an element, they're diatomic, right? So we have to balance this. So we need 2 there and 3 there. But remember, we want to determine the change in enthalpy for 1 mole of the product. So we're going to change that to 1. We're going to divide everything by 2. Okay, and that's going to become a half. So we're going to end up with 1/2 N2 as a gas plus 3/2 of H2 are going to give us NH3 also as a gas, right? And I can look up on the tables that I gave you, the thermodynamic data, and these are all in alphabetical order by the substance. So there's 2 here. One is for ammonia as a gas, and one is for aqueous ammonia. So we want to use ammonia as a gas. So the change in enthalpy of formation for that in kilojoules per mole is negative 46.19. So that's what we're going to use. And that's going to be equal to minus 46.19 kilojoules per mole of a reaction. Okay? We're going to do the same thing with SO2. So why don't you try doing it for the 3, and then we'll come back and see whether I got the same answers. Okay, so go ahead and pause and try this. So sulfur is going to be in its solid state, and oxygen will be as a gas in its normal state, and it's going to make SO2. I don't have to change anything with my coefficients because it's already balanced. And if I look up the thermodynamic data for SO2, under sulfur, SO2 as a gas is going to be minus 296.9 kilojoules per mole. Okay? Alright, so that's going to be minus 296.9 kilojoules per mole of reaction. Alright, I'm going to have rubidium chlorate over here, and its standard state is a solid, and it's going to be formed from rubidium plus chlorine, which would be Cl2 as a gas. Rubidium is going to be a solid because it's a metal, and O2, which is also a gas, of course. And if I balance this, I'm going to, let me see, I'm going to need to double this to get 6 oxygen, so that'll be a 3. I need 2 rubidium. Okay, so in order to get this to be a 1, and I will draw this in a different color, I've got to divide everything by 2. So it's going to be 1/2 of that, and that's going to become a 1. Okay, and if I look it up on the table, I will minus 392.4 kilojoules per mole. Okay, and the last one here is we are making ammonium nitrate, which is going to be, looks like it's a solid, and I'm going to make that from nitrogen, hydrogen, and oxygen, all of which will be gases at their standard states. And I'm going to need 2 nitrogens. I've got that. I'm going to need, alright, so I've got 3 oxygens. I'm going to need to double that to get that to be 3. So this becomes 4 and an N2. So I'm going to have to half all of these. So I'm going to end up with 1/2 N2 plus 2 H2 plus 3/2 O2 will give me NH4 NO3 as a solid. All of these are reactants or gases. And if I look up ammonium nitrate on the table of enthalpy of formations, I get minus 365.6 kilojoules per mole. And that's change in enthalpy of formation. Okay, so hopefully you get the idea. Alright, so we have some assignments to do for that. Next we want to talk a little bit about Hess's law. So what Hess's law says, that if I'm making a product, it doesn't matter whether what route I take. The enthalpy change, let me change my color of my pen here. The change in enthalpy is going to be the same regardless how I get from my reactants to my product. All it depends on is what is the enthalpy of my reactants and what is the enthalpy of my product, regardless of the route I take. So if I take a route between these reactants and products that involves one step, my enthalpy is going to be delta H1. If I take a process that takes me through an intermediate and then onto the product, that's going to be delta H2 plus delta H3. And what Hess's law says is that these are going to be equal. This is equal to this. And delta H4 plus delta H5 plus delta H6 are also going to be equal to these. So all of these are equal to each other. Doesn't matter what path I take. All I need to know is what the enthalpy of the reactants are and the enthalpy of the products, and it's the difference in those that's going to give me my enthalpy for the reaction. Okay. So Hess's law, and Hess's law says that the change in enthalpy of a reaction is simply the change in enthalpy of the products minus the change in enthalpy of the reactants. And these boxes I meant to cancel out. They shouldn't be there. So the change in enthalpy of the products, which I can find on that table that I gave you, minus the enthalpy of the reactants. Okay, so let's see how we're going to use this. So given the information above, calculate the change in enthalpy of the reaction for the following chemical reaction given to us right here. Okay. So you should always, on the AP exam, so the change in enthalpy of the reaction is going to be the change in enthalpy of the products minus the change in enthalpy of the reactants. Just doing that, even if you don't do anything else, gives you some credit on the AP exam. So I'm going to go ahead and say that it's going to be the change in products are going to be these four. So it's going to be the change in enthalpy of Al2O3 plus change in enthalpy of AlCl3 plus the 3 times the change in enthalpy of NO, because there's 3 of them. I got to take into account the stoichiometric coefficients, right? Plus the change in enthalpy of 6 times the water's enthalpy. Okay? Minus the change in enthalpy of the reactants. Now, this is an element, and remember what we said, it's an element in its standard state, and that delta H is equal to 0. So all I need to subtract here is 3 times the change in enthalpy of ammonium chloride. Okay? So now I can plug in the numbers, and I'm going to have minus 1676 kilojoules plus a minus 704 kilojoules plus 3 times 90 kilojoules plus 6 times minus 242 kilojoules. And then we subtract from that the reactant, which is going to be, okay, that was the reactant, 3 times, no it's not, 3 times minus 295 kilojoules. And that's going to come out to be what's listed on the bottom of the paper, minus 2679 or so kilojoules per mole of reaction. Now, one thing you want to be careful of when you're looking up these values, now they won't always be given to you on the test or in your quest homework. You have to look them up in the tables. So one of the things you want to be careful of is H2O will be listed as a gas and it will be listed as a liquid. So you always want to make sure you're picking the right one. And here it says it's a gas, so I have to use the value for a gas. Okay, exercise 12. Occasionally, not all values are found in the table of thermodynamic data. For most substances, it is impossible to go into a lab and directly synthesize a compound from its free elements. So the heat of formation for the substance must be calculated by working backwards, and we can do this because of Hess's law, using its heat of combustion, for instance. So we want to calculate the heat of formation of glucose given the combustion reaction above and its change in enthalpy. Okay? So be careful here because we show, this reaction shows heat as a product, so that heat is negative. It's 2800 kilojoules. The delta H of the reaction is minus 2800 because it shows the heat as a product. Okay, so the change in heat of reaction, which is minus 2800 kilojoules, is going to equal the delta heat of the products, delta heat of the products minus the change in enthalpy of the reactants. And that's going to be 6 times CO2s plus 6 times H2Os minus the enthalpy for the reactants. And here I have glucose, but this is the element in its standard form, so that's 0. So I can leave that out. So minus C6H12O6. Okay. And now what I am solving for is this, right? I know everything else. So I'm going to rearrange the equation to solve for the heat of formation of this. So I'm going to add 2800 kilojoules to each side, and I'm going to add C6H12 to each side. And what I end up with is an equation that says C6H12O6 equals 6 times CO2, which is, the value there is minus 393.5, plus 6 times the value of water, which is minus 285.8, plus I've added the 2800 kilojoules. And if I plug all that in, I'm going to get, let me just make sure I set this up right. Yeah, and we should get what's down here, which is 1276, negative 1276 kilojoules per mole. Okay? 6 times minus 393.5 plus 6 times minus 285.8. Okay. The thermite reaction, if you've seen it, it's a very exothermic reaction. It spews iron all over the place. Occurs when a mixture of powdered aluminum and iron 3 oxide is ignited with a magnesium fuse. The enthalpies of formation using enthalpies of formation, calculate the standard change in enthalpy for this reaction. Okay, so the change in enthalpy of the reaction is going to be the change in enthalpy of the products minus the change in enthalpy of the reactants. And in this case, the product is Al2O3. Iron is 0, right? Because it's an element in its standard state, minus Fe2O3. And these are enthalpies I'm talking about. This is also 0, right? So I have to go to my table of thermodynamic data. And when I do that, Al2O3, let's find that on here. Al2O3 is minus 16698 kilojoules per mole. And I'm just going to look up Fe2O3 while I'm here. Fe2, let me see, Fe2O3 as a solid is minus 822.16 kilojoules. Alright, so let's go back here. Alright, so Al2O3 was minus 1669.8 kilojoules, minus iron 3 oxide was minus 822.16 kilojoules, and the difference there is going to be minus 850. It must be going to 2 sig figs. Looks like 3 sig figs kilojoules. It doesn't come out exactly that, but it's going to be close enough. It's certainly within that 1% that Quest needs. Okay. Do one more problem. Okay. So what we learned from Hess's law is that enthalpy is independent of the reaction pathway. If you can't find a combination of chemical if you can find a combination of chemical equations that add up to give you the desired overall reaction, you can just sum up the delta H's. Okay. So let's just go ahead and do it, and then you can read those rules up at the top. So here I have 3 equations, and I'm going to try to use the data from those 3 to figure out what the change in enthalpy is for this. So what I have to do is rearrange the equations if I need to. So I have H3BO3 as a reactant. So here it's a reactant, so that looks good. B2O3 needs to be a product, and here I got B2O3 as a product. And I have water as a reactant, as a product here. It's a product here and here, but not here. And I have this intermediate B2, H2B4O7. I know it's an intermediate because it doesn't show up anywhere in the overall reaction. So what I need to do is flip this equation. And I know I have to flip this one and not this one because I need to have water on this side, and I need to leave B2O3 on the product side. So I'm going to rewrite that equation. Turned around, HbO2 gives me H2B4O7 plus, H2O. And when I do that, I have to change the enthalpy. It's going to just change the sign. If I'm going backwards, it's going to be a plus 11.3 kilojoules per mole. Okay. And so I'm going to cross this out because I'm not using this one anymore. Alright, so I'm not quite there yet because, let me see, I need 2 H3BO3s, so I'm going to need to double this. Okay, and when I do that, I end up with 2 of those and 2 of those, but I have 4 HbO2s here to cancel and 2 here, so I'm going to cut this one in half. Okay, when I do that, I end up with 2 of that, 1/2 of that, and 1/2 water. And I have to be careful because I want to divide this by 2 now. Make sure I'm adjusting the enthalpy as a result. Alright, so now I can cancel out my HbO2, but I don't have enough H2B4O7. I've got 1 here and 1/2 here. So I'm going to have to make this 1/2 also. The whole thing. So this divide by 2 is going to be 1. This is going to be 1/2. Alright, so let's see where we are now. So we have 2H3BO3. I have 2HBO2 canceling with 2HBO2. I have a half H2B407 canceling with a half H2B407. And on the product side, I have 2 plus a half, so that's 3 waters. Okay. So now I need to make sure I adjust all the enthalpies. So this one, I had doubled it, right? So I'm going to multiply this times 2. This one I got rid of, so I'm going to just take that one off because I reversed it, right? Here I multiplied this times a half, so I'm going to multiply this times 0.5. And this one was reversed and halved. Okay, so my total change in enthalpy for the reaction is going to be minus 0.02 times 2 plus 17.5 times 0.5 plus 2 times 11.3, and these are all kilojoules, and if I multiply and add those up, I should get 14.4 kilojoules per mole of reaction. Okay.